All right. So the reason that I wanted to, because I know it seems kind of weird that we're coming back to Extrema after going to concavity. So you might be wondering, why didn't we do this right after? Why didn't we do this lesson right after we finished talking about Extrema? And the reason why is because concavity can play into Extrema, right? If we have a function that is concave down, in other words, if the second derivative is negative, that means that we're going to have a maximum, right? So concave down produces a maximum. Okay, and then similarly, if we have a function that's concave up, right? If it's opening up, or if it's kind of that bowl shape or U shape, then we're going to have a minimum. Okay, so concave up, or in other words, where the second derivative is greater than 0 or positive, that's going to produce a minimum. Okay, and it's a little counterintuitive because so concave down produces a max, so that's so sometimes you might think of down as a minimum, but concave down means that we have this hill shape, or upside down U or N, or whatever you want to think of shape, and so that means we're going to have a peak. And when we're concave up, sometimes you think maybe up as a max, but concave up just means it's facing up, which means you have a valley down there below, and so you end up with a minimum. Okay, all right. So the second derivative test basically entails, all we really have to do is, once we find our critical points where the derivative equals 0, we can just plug in the second derivative, or excuse me, we can just plug that value, the critical point value, into the second derivative and see if the second derivative is positive or negative at that point. Or it could be 0, in which case it'll be inconclusive. So, and that's when you might have to go back to the first derivative test. Okay, all right. So here's the idea. Theorem 4.11. Suppose that f primed at c is 0, so we have a critical point. And notice that we're not testing the places where f primed is undefined, because if f primed is undefined, f double prime won't exist, and so we can only work with the ones where we have 0. So once again, the first derivative test is a little more comprehensive in that way, but most of the time, especially with polynomials, we're going to be dealing with 0 values for our critical points where the derivative is 0. So anyway, so we figure out where the derivative equals 0, and then and we want to make sure that f double prime is continuous over whatever interval that contains c. All right. And so then if the second derivative is greater than 0, which means concave up, right? Then that's when we have a local minimum, just like we talked about, because it's going to look like that, right? If we have a second derivative at that critical point that's less than 0, that means it's going to be concave down, right, like this, and that means we're going to have a local maximum. Okay, and then if the second derivative is 0 at that point, then the test is inconclusive. And there could be a few things. It could actually be a max or a min still, or it could be one of these kind of fake out points where it goes up and then it keeps going up. And there's a few other possibilities as well, but it's inconclusive. Okay, so you can put NEI, like not enough information, or you can put inconclusive, or something like to that effect is fine. All right, so let's try out this example here. So with the second derivative test, we want to find the first and second derivative test. We find the first derivative so that we can know where our critical points are. Okay, so f prime of x is going to be 5x to the fourth minus 15x squared, right? Okay, and then I'm also going to find the second derivative. So the second derivative will be 20x cubed minus 30x, right? Okay, so first of all, let's find our critical points, or let's find where the derivative equals 0. So I'm going to set f of x equal to 0. I'm going to factor out a 5x squared here. That's the greatest common factor. And so I'll end up with x squared minus 3, right, on the inside. Okay, and so then I can set these equal to 0. So this the only way this can be 0 is if x is 0, right? So x equals 0 is going to be one of my solutions. And if you're not sure, you can definitely set this equal to 0 and solve. You divide by 5, you get x squared equals 0. And then you would take the square root of both sides, so you get plus or minus 0, which, those are one and the same because 0 is neutral. So, so you end up with x equals 0. Here, if we set this equal to 0, we would add 3 to both sides, so we'd end up with x squared equals 3. Then we would take the square root, and we'd end up with x equals plus or minus root 3, okay? All right, so we actually have three points where the derivative equals 0, right? 3 critical points. And so we want to plug all 3 of those in, all right? So I'm actually going to take away this plus or minus, or I'll leave it, let me just leave it here, and then I'll just write it here twice. Positive root 3 and negative root 3. And we have 0. Okay, so those are our critical points. So now what I want to do is I want to find the second derivative at those points. Okay, so I'm going to find the second derivative at 0. So I just plug it in here. And if I plug in 0 for x, these will both turn to 0, right? And so I'll end up with 0. Okay, so that means that this is inconclusive. Inconclusive. Okay, all right. And we'll come back to that here in a second. Then we can find f double primed at positive root 3. Okay, so let's do a little math here. If I do f double primed at positive root 3, that would be 20 times root 3 cubed minus 30 times root 3. And you can plug that in your calculator, whatever you want to do. But root 3 cubed is going to be 3 root 3, right? So 3 root 3 times 20 is going to be 60 root 3. And then it's minus 30 root 3. And so that'll be positive, right? It'll be positive 30 root 3. And yeah, and so anyway, so that's going to be greater than 0. And so that means we have a minimum, right? Remember, if it's greater than 0, that means it's concave up. And so that means it's going to be a minimum. Okay, so we have a minimum at square root of 3. And then the last one, let's check out f double prime at square root negative 3. So that would be 20 times negative root 3 square, or cubed, excuse me, minus 3 times, or 30 times negative root 3. And so this would end up being negative 3 root 3 when we cubed it. So it would be negative 60 root 3. And this will come out to positive 30 root 3 because a negative times a negative. And so we'll end up with negative, doesn't really matter what it is, but it'll be negative 30 root 3. And so therefore, this is going to be, since it's negative, that means it's downward facing, concave down. And so that means since this is less than 0 or negative, that means we're going to have a max. Okay, so we have a max at negative root 3. All right, so that's how we use the second derivative test. Now, since this was inconclusive, now we can fall back on the first derivative test if we wanted to. So we could plug in a value that is between negative root 3 and 0. So like negative 1 would work. Negative 1 is between those two. So if I found negative 1 in the first derivative, if I plugged in negative 1 there, it would basically be 5 minus 15, so it would be negative on the left side of that. Okay, and then if I, between 0 and root 3, or 0 and positive root 3, if I plugged in a positive 1, right, that would be between there. So then I would get same thing, 5 minus 15, so that would be negative. So it's one of those fake outs where the slope is negative, it flattens out, and then it gets negative again. Okay, and so yeah, so it's neither, right? All right. So second derivative is nice because you can just plug it in, and you don't have to show all this work here. But you can just plug those points into the second derivative and then just see if it's positive or negative, rather than finding out all the intervals and then finding out what what the sign is for the derivative between those intervals. But use whatever method you like. Like for me, I just I'm a little more or the second derivative test just feels a little better for me, and it's my preference. But your preference can be totally different. You can like the first derivative, and you can use that as much as you want, and you can use that in place of the other the second derivative test if you'd like, for sure. So either one, you can use them both. Sometimes you might need them both, like we saw here, and so yeah. Anyway,